So in this video, I'll discuss how to identify and generate structural isomers. So before we get into an example, of course, we need to know what are structural isomers. Anytime you see the word isomer, that indicates that we're dealing with molecules that have the same formula, but something about them is different. What's different depends on what type of isomer we're dealing with. So in the case of structural isomers indicate that they have the same formula, but the atoms are connected differently. So for instance, if you were simply told that a molecule has a formula of C4H10, based on this general molecular formula, we know that we're dealing with an alkane, so a saturated hydrocarbon. So with that alkane, just because it has 4 carbon, 10 hydrogen, doesn't mean that it has to exist this way. It could, because if we look at this carbon has 3 hydrogen, this carbon has 2, this carbon has 2, this carbon has 3. So we're dealing with the molecule that has 4 carbon. So each point represents a carbon. And if we add up all those hydrogen, we have a total of 10 hydrogen. But we could have also shown the molecule this way. So if we look, we have 1, 2, 3, 4 carbon. And if we look at our hydrogen, the carbon to the left has 3 hydrogen. The middle carbon only has 1. Top carbon has 3. The right carbon has 3. And I'm getting these numbers because we know that carbon always has 4 bonds. So any bonds that we don't see to other atoms means that they are bonded to hydrogen. Because in a skeletal structure, we do not see the bonds between carbon and hydrogen. So that's how I came up with those numbers. But for that second molecule, I have those 4 carbon. If I add up the hydrogen, it also totals 10. So these both have 4 carbon, 10 hydrogen, but the atoms are connected differently. The structure to the left, we have carbon 1. I can just number them. 2, 3, and 4. So carbon 1 was bonded to carbon 2. Carbon 2 was also bonded to carbon 3. Carbon 3 was bonded to carbon 4. But if we look at the structure to the right, carbon 1 was still bonded to carbon 2. Carbon 2 was still bonded to carbon 3, but carbon 3 was no longer bonded to carbon 4. Instead, there was another carbon bonded to carbon 2. That wasn't carbon 3. So that tells us that these atoms are no longer connected the same way. This is what a structural isomer represents. So these molecules have the same formula, but the atoms are connected differently. So as a result, they're going to have different names. The structure to the left is butane. You'll also hear it referred to as N-butane just because it's a straight chain, but I'll just simply name it butane. The structure to the right is 2-methyl-propane. I know this is the name because I have 3 carbon atoms in my continuous chain. So my longest chain has 3. I have 1 carbon branching off of that, which represents a substituent. So that's where my methyl comes from. Those 3 carbons in a continuous chain was the prefix prop. The A and E told me that there were only single bonds between those carbon atoms. And then this 2 tells me that that methyl is branching or attached to carbon 2. And so that's how I come up with that name. And so if you notice with structural isomers, even though they have the same formula, the molecules are named differently. So again, structural isomers, same formula, atoms are connected differently. So as a result, they're going to have different names. Now in the case of butane, these are the only 2 structural isomers for this molecule that has 4 carbon, 10 hydrogen, only those 2. But as the number of carbon atoms increases within a molecule, you're going to see more and more structural isomers. You can also see where in some cases, you may be looking at 2 different classes of molecules. So for instance, if we were looking at C4H8, that's no longer an alkane, but instead it could represent an alkene. So I could have had cyclobutane. I could have had methyl cyclopropane. These both have 4 carbon, 8 hydrogen. But I could have also had an alkene. I could have had 1 butene. I could have had 2 butene. I could have had 2-methyl 1-propene. And these all have 4 carbon and 8 hydrogen. So just because we're dealing with structural isomers doesn't mean we have to deal with only one class of compound. We have to just think about what class would have this general type of molecular formula, and then how can we come up with different combinations, different arrangement of atoms in order to make new compounds. And so we'll work through an example. So here it says that there are 9 structural isomers of C7H16. Draw the structure and give the IUPAC name of each. So this problem gives us a clue that we're dealing with 9 structures, but they all should have 7 carbon, 16 hydrogen. The easiest way to generate structural isomers, once you know what your formula is supposed to be, start with that. Because there's only one way that we can have a straight chain alkane, in this case, and represent 7 carbon, 16 hydrogen. Everything else is going to have to be a branched alkane. And so, again, I know that C4H10 and this C7H16 represent alkanes because alkanes have the general molecular formula of CN, I wrote 4, but CnH2n plus 2. So N is just how many carbon. So from when we had 4, N was 4, 2 times 4 is 8, 8 plus 2 is 10. So that's how I knew that was an alkane. In the case of this molecule, we have 7. 7 times 2 is 14, 14 plus 2 is 16. So I know that based on this molecular formula, it can only represent alkanes. And so when we look at this, we can think about that when generating these 9 structures. Again, there's only one way we can have a straight chain alkane. And so my recommendation is that you start with that. So start with 1, 2, 3, 4, 5, 6, 7 carbon atoms. That's the longest parent chain. I don't have to add any substituents because I've already accounted for those 7 carbon. If you were to go through and count the hydrogen, I'll do that for this one. This carbon has 3 hydrogen because I can only see 1 bond, so there are 3 that I do not see. Oops. This carbon has 2 hydrogen. This one has 2. I see 2 bonds, so there are 2 that I do not see. All of these carbon atoms in the middle have 2 hydrogen, and then the carbon atoms on the end both have 3. So if we were to add them up, I can highlight the carbon as well. Each point, so that's 1, 2, 3, 4, 5, 6, 7 carbon. If I were to go and add up the hydrogen, I have 3. So 3, 5, 7, 9, 12, 13. Did I add them wrong? I added wrong. Sorry, let me start over. 3, 5, 7, 9, 12, 14, 16. Let me get myself back on track. So 7 carbon, 16 hydrogen. So I do have the correct number and type of atoms present. If I look at the name of this is heptane. Hept is the prefix for 7, ane because we only have single bonds. So there's no other way that I can make a structural isomer that has a total of 7 carbon atoms but has a parent chain of 7. So what that means, once I have that straight chain, then I have to start reducing my parent chain. Because right now my parent chain is 7 with no substituents. So then the next parent chain that I can have, I can deal with the parent chain that has 6 carbon. And so instead of the 7 carbon atoms in a straight chain, I would draw 6 across. So 1, 2, 3, 4, 5, 6. So I know my parent chain is going to be hexane, but if I stop here, I only have 6 carbon. So what that means is that I need to add a substituent. So I can choose to add a methyl. I cannot add my methyl at carbon 1 because that simply made 1, 2, 3, 4, 5, 6, 7 carbon atoms in a straight chain. So that leaves me back with heptane. So I can't put my methyl on carbon 1, but I can put my methyl at carbon 2. And so if I look, I have 1, 2, 3, 4, 5, 6, 7 carbon. If I go back and look at my hydrogen, this carbon has 3 hydrogen. This next carbon only has 1. The carbon above it has 3. And if we go back on our chain, we have 2 hydrogen, 2 hydrogen, 2 hydrogen, 3 hydrogen. So then if I add up those hydrogen atoms, I have 3, 4, 7, 9, 11, 14, 16 hydrogen. So again, I have the same formula, but I'm going to have a different name because now my parent chain is different and I have a substituent present. So now my parent chain, I only had 6 carbon atoms in my parent chain, so that means that my parent chain was hexane because hex is 6, ane because I only have carbon-carbon single bonds. Remember, when you're naming parent chains, you can go from left to right or you can go from right to left. So I'm going to erase some of this just to make it a little clearer. So if we number it from right to left, then we can indicate where our substituent is located. We can do the same thing from right to left as left to right. So left to right, 1, 2, 3, 4, 5, 6. Right to left, 1, 2, 3, 4, 5, 6. So of course, when numbering, you want to give your substituent the lowest number. So we would end up with 2-methyl hexane, all one word. But then I can think about, if I had the methyl on carbon 2, that gave me 1 extra carbon to not add it to that parent chain, but it didn't have to be on carbon 2. What if I moved it to the next carbon? So if I put the methyl here, it's no longer connected the same as before. Still has 1, 2, 3, 4, 5, 6 carbon atoms as the parent chain. And we can see, because we're closer to the right side, now we have 3-methyl hexane. So still a different molecule. You can check to see if you can get it another way. So what would happen if I put it here? You want to be careful, because some would simply say, yes, now we have 4-methyl hexane. But what you have to remember is that we can number from right to left or left to right. So 1, 2, 3, 4, 5, 6. If we're going from left to right, 1, 2, 3, 4, 5, 6. If we go from right to left. So this is actually 3-methyl hexane. So this is the same as the one right above it. So this would not be a different structural isomer. That is the same as the molecule above it. And so once we've determined that, okay, I can't come up with any other stereo or any other structural isomers that have 6 as the parent chain, then I can ask myself, what would happen if I go down to 5 as the parent chain? So I put my 5 carbon atoms in my parent chain. That means I need to add 2. So I have different ways that I can add 2, because we do have one substituent that has 2 carbon, which is the ethyl, or I can look at adding 2 methyl groups. But when you're adding the ethyl, you have to be careful, because we know that we can't add it to carbon 1, because if I add it to there, 1, 2, I've extended my parent chain. So now I'm back to heptane again. But I also cannot add ethyl to carbon 2, because if I add it here, 1, 2, I've extended my parent chain. Because now you would have 1, 2, 3, 4, 5, 6. We will be back to that 3-methyl hexane again. So be careful where you're adding things at. So maybe I can add the ethyl to the middle carbon. When I add it to the middle carbon, I have 1, 2, 3, 4, 5 if I go straight across. But I could have also said 1, 2, 3, 4, 5 by going down. It doesn't matter which way you go. You get 5 as your parent chain, which indicates that our parent chain is pentane, 5 carbon atoms that have only single bonds. But, so that accounts for those 5. But we still have this one group, one substituent branching that has 2 carbon atoms. So that means that we have an ethyl group. So ethyl pentane. But we have to indicate where that ethyl pentane is located. Again, I can number from left to right. I could also number from right to left. In this one, it doesn't matter, because both give me 3 as the location of that ethyl group. So we still have, if I were to go through and clean this up so that we can go back and count, since we're dealing with a new parent chain. We know we have 7 carbon atoms, so we know that. because we have those 1, 2, 3, 4, 5, 6, 7 total. If we look at our hydrogen, we have 3 hydrogen, 2 hydrogen, 1 hydrogen, 2 hydrogen, 3 hydrogen, 2 hydrogen, and 3 hydrogen. So if we were to go and add them up, we have 3, 5, 6, 8, 11, 14, 16. So again, 7 carbon, 16 hydrogen. We have a different structure. So that's our fourth one. There's no other way that we can add an ethyl, because if we add an ethyl to this carbon, we're back again to 3-methylhexane, because it would extend our parent chain. So we have no other ways that we can show 5 as the parent chain, but have a substituent of ethyl. So now we can look at what would happen if we add 2 methyl groups. So again, we cannot add methyl to the first carbon, to any of those N carbons, because it would extend a parent chain. But we could add a methyl to carbon 2. We could add a second methyl to carbon 2. So I can actually add both of my methyl groups to that carbon. When I do that, I end up still with 5 as my parent chain. I still have pentane, 5 carbon atoms connected only by single bonds. Now I have 2 substituents. And so if you're having trouble distinguishing between these 2 substituents, box off your parent chain. So I can box it, or I can highlight it so that I can see what is already accounted for. So any carbon in that highlighted region is already accounted for. So then I have this branch or bond sticking off. I have this branch or bond sticking off. That lets me know that I have 2 substituents. They each only have 1 carbon. So therefore, I'm dealing with 2 methyl groups. So how do we indicate 2 of the same? Instead of saying methyl, methyl, we use those prefixes, di, tri, tetra, so on and so forth. So di tells me that I have 2 of the same. So dimethylpentane. But I have to indicate where are both methyl groups located. Even if they are on the same carbon, I have to indicate where they are both located. So both of these are on carbon 2. And I know that because I can number from left to right. I can number from right to left. But that's not the only way we can have 2 methyls. I could have had 1 methyl on carbon 2, and maybe I had another methyl here on carbon 3. So I'm still dealing with a pentane. I'm still dealing with 2 methyls that are present. So I'm still dealing with dimethyl, but now I have 1 on carbon 2 and I have 1 on carbon 3. So then I would have 2,3-dimethylpentane. So now we're up to 6 of the 9. But again, think about, are there other ways? So I had 2, 2, I had 2, 3. I still have other carbons present. So maybe I can have 1 on 2 and 1 on 4. That's still a different molecule, because now I still have 2 methyl groups, but now 1 on 2 and 1 on 4. So now I have 2,4-dimethylpentane. So again, we can go through and add all of these. If you don't want to count all the individual carbon atoms, look at your name. Pent accounts for 5 carbon. Meth accounts for 1 carbon. But this 2, the di, tells me I have 2 of them. So 2 times 1 is 2. Plus 5, I've accounted for all 7 carbon. So your name should still account for all of those carbon atoms. And so then you want to look, are there any other ways that I can have 5 carbon atoms as my parent chain, but include 2 methyl groups? So I can't say that now I have 2, 5, because that extends the parent chain, and now we're actually forming 2-methylhexane. So I can't do that. So what if I move this one? So all the previous ones were showing that first methyl on carbon 2. Then I put my second on carbon 2. Then I move my second one to carbon 3. Then I move my second one to carbon 4. So what if I put my first one on carbon 3? If I put my second one on carbon 2, I can't use that one because again I have 2, 3. So I can't use that one. But what if I put my first one on carbon 3 and my second one on carbon 3? I haven't had that one yet because now I have 3 and 3 as far as my locator numbers for both of those methyl groups. So now I have a different molecule. Now I have 3,3-dimethylpentane. So then What if I leave it on 3 and move it to 4? Even though I said 4, if I were to actually go through the rules of naming, that wouldn't be 3, 4. That would be 2, 3 again. So what that tells me is that there are no other ways that I can show 5 as my parent chain, but add 2 methyl groups. So I can't show 5 and add an ethyl. I can't show 5 and add 2 methyls. So that means that now I need to move down to the next parent chain. So instead of 5, now I'm going to have 4. So if my parent chain has 4, that means I still need to add 3 other carbon. So you have different ways you can do this. You can add a propyl. Not saying that we can do it in this case, but you can add a propyl to add 3. You can add an ethyl and a methyl, which adds 3. Or we can add 3 methyls. And so in this case, if I try to add a propyl anywhere, so 1, 2, 3, that takes me back to heptane. So I can't do that. 1, 2, 3. That takes me back to 3-methylhexane. So I can't do that. Same thing if I move it here. 1, 2, 3. I'm back at 3-methylhexane. So I cannot add a propyl to this parent chain. So then I need to look at, well, can I add an ethyl and a methyl? Just as I couldn't add a propyl at the end, I can't add an ethyl. If I go to the middle carbon and try to add an ethyl, I can't do that either because it extends my parent chain. So I can't do an ethyl and I can't do a methyl to give us 3. So what if I try to add just individual methyl groups? So this carbon can have 2. Because remember, carbon can have 4 bonds, but only saw 2. So that means that we could form 2 more. And that means that I could put a third one. The only other place I can put it would be here. So if I look, I have 1, 2, 3, 4, 5, 6, 7 carbon. If we were to go through and add up those hydrogen again, this carbon has 3. This one has 0 because it already has 4 bonds. This one has 3. This one has 3. This one has 1. This one has 3. This one has 3. So if we were to go up and add them all together, we have 3, 6, 9, still 9, 10, 13, 16. So we still have our 7 carbon, 16 hydrogen. If we were to go through and name it, we have 4 as our parent chain. We have 3 branches, so 3 substituents sticking off of that parent chain. So that means that now we have a parent chain that has 4 carbon. So parent chains with 4 carbon represent butane, 4 carbon with only single bonds. But now we have 3 methyl groups. So we won't call it dimethyl-methyl. Instead, we would simply call it trimethyl. Tri is the prefix for 3 of the same. So I have 3 of the same substituents, 3 methyls. So I have to indicate where all 3 are located. Just as before, I have to indicate the locator number, and I want to use the lowest numbers possible. I can number from left to right. I can number from right to left. If I go from left to right, 1, 2, 3, 4. If I go from right to left, 1, 2, 3, 4. So when I look at this, I have 1 methyl on 2 if I go from left to right, a second methyl on 2, and then the methyl on 3. I should have switched back to the other color. Let me rewrite that so I stay consistent with my colors. So left to right, 2, 2, 3. If I go right to left, I have 2, 3, and 3. If you're struggling with which way, just take these numbers and add them together. 2, 3, 3 gives me 8. 2, 2, 3 gives me 7. I get 2 lower numbers by going from left to right. So what that means is that the name of this compound is 2, 2, 3 trimethylbutane. So that gives us our 9 structural isomers. There's no other way that I can do this because if I move 2 to the opposite side, I'm going to end up just numbering from right to left. So that is all that I can do. I can't go down to 3 as my parent chain because if I have 3 as my parent chain, that means I need to have 4. I'm going to go back to this and just to show that. So if I had 3 as my parent chain, I need to add 4. I can only add 2. I can't add 2 anywhere else unless I extend my parent chain. So again, when you're determining structural isomers, start with your straight chain and then from there simply reduce the number of carbon atoms in your parent chain and start adding substituents. So in other words, you can only have 1 straight chain And then from there, you start making branched, in this case, alkanes. Figure out how many and all that you can do with that specific parent chain, and then decrease your parent chain and start adding additional substituents. So I hope this helps. If you have any questions, please let me know. Thank you.